Hello, welcome back to part 2 of lecture 14 of SYDE 552. Previously we covered ion channels in cell membranes and neuron membranes and the role they play in changing the membrane potential, and also how we would integrate them into a circuit model of the cell membrane potential. And now we're going to cover models of ion channel conductance that were developed by Hodgkin and Huxley to explain how conductance changes as a function of membrane potential. In biology, ion channels are gated, and that is to say they can open and close. And that gating of membrane channels depends on changes in the protein structure. And so what we see here is an ion channel that's resting, it's closed, there's an activation gate that is blocking the flow of ion through the channel, and then because of a change in the polarization of the cell membrane, this gate opens, ions begin to flow, but then at some point the cell is inactivated by another mechanism which blocks off the flow of ions through the channel. So this gate here, an activation gate, there's the activation gate which functions to open. As it becomes more active, it lets ions in, and there's the inactivation gate which, as it becomes more active, slows the flow of ions or stops the flow of ions coming in. And so a gate may swing and partially block an ion channel, and variable conductance channels may have one or more of these gates that may change shape in response to voltage or neurotransmitters. So to model variable conductances, what we're going to do is we're going to start by picking an ion channel. Next, we will figure out how many independent gates it has from empirical observations of the protein structure. And usually this is about 1 or 2 gates. Then we're going to assign a variable S to each of these gates. And write a differential equation to describe the dynamics of the state variable, S ds dt, as a function of time and voltage. Then we're going to write an equation, G ion, of these state variables, that is to say the conductance of the ion channel, that describes how it works, how the conductance changes as these state variables change. Then we will interpret that conductance, G ion, as a probability that a single ion channel molecule is open, or a fraction of all the ion channels are open in a specific region of the membrane. Here we see 2 images of the protein structure of a sodium channel here on the left and a potassium channel on the right. Also below we see the equations for the voltage-dependent conductance of these channels. With the sodium channel, the conductance is a function of 2 state variables, M and H, which are themselves functions of the membrane voltage, V, and a constant term, GNA, which acts as sort of a baseline conductance for the channel. And then here for the potassium channel, we see that it is a sort of baseline conductance, GK, and then the state variable N raised to the power of 4, which is also a function of voltage. And M here is the sodium channel activation state variable. H is the sodium channel inactivation, like the activation-inactivation gates we saw on the previous slide. And then N here is the potassium activation variable, or channel. These are unitless quantities that take on values between 0 and 1, or 0 and 1 inclusive. And they give us an indication of 1 is how they are completely active, and 0 is they are completely inactive. So a completely active activation channel would let ions in, and an inactivation channel would block ions from coming in. So just to give a quick review of our goals here, is that what we're trying to do is build a neuron model, which is a function of some set of state variables, like we had in the past, a state variable like the membrane voltage. And we are going to, and that these variables will describe in detail the dynamics of the cell. And we're particularly interested in displaying the dynamics that give rise to the actual action potential shape. Right? We want to build a circuit like we did with the LIF neuron, where the capacitor is charged by several ionic currents, each with an associated resistor or conductance, and a battery. And we want those battery voltages to be fixed based on the reversal potential for each ion, but we want the resistors to change based on the voltage of the cell. Each of these resistors should be modeled by the interaction of gating subunits within the ion channel, and each gating subunit has in turn its own state variables whose dynamics depend on voltage and time. And the neuron models that are structured in this way, that meet these criteria, are generally referred to as Hodgkin-Huxley models. So we are going to build a dynamic model of the gating state variables, and those variables are M, N, and H. Right? So N for the potassium channel and M and H for the sodium channel. The dynamics of the gating variables and their interaction is going to produce the core voltage dynamics of the cell, including the full action potential nonlinearity. Now, Hodgkin and Huxley came up with the 6 equations here that satisfied this goal. And the form and parameter values were fit to empirical data they collected from experiments with actual neurons. And a closer look at the biophysics actually somewhat justifies some of the choices that they made here in their modeling, and so that's kind of a comforting thing to know. And just as a note of caution before we dive into the equations, that there are 2 formulations, the transition rate formulation and the steady state formulation. We will show you both equations, but different people may use different ones depending on what they're trying to communicate. So if you see some equations that look strange, or they weren't what you were expecting, depending on what you're reading, just keep in mind these different formulations. Also, sometimes people use different variables for the quantities involved here. So anyway, we have these gate state variables, and in this top equation here, S can take on the value of M, N, or H, and in particular, this thing describes how active, or how the activity of this gate variable changes as a function of voltage, and voltage is communicated through these 2 terms here, alpha, beta, where alpha specifies the forward transition rate and beta specifies the backward transition rate. So alpha is trying to describe how the propensity for the ion channel to become open, and beta is describing the propensity of the, I should say, alpha is trying to describe the propensity of the gate state variable to become more active, and beta is describing the propensity of the gate state variable to become less active, that is to say, closer to 0. And what this activity means is that we can understand this function here as saying that the probability of becoming active is equal to, we can understand S taking on a value between 0 and 1 as being like the probability that this state variable is active, and so 1 minus would be the probability that it's inactive. So we can say, what's the probability that you're inactive times the probability that you will become active based on the voltage. And then this is counteracted by this term where S is saying it's the probability that you already are active times the probability that you will become inactive as a function of the voltage. And so we can see how the voltage through these 2 terms is driving the dynamics, moving the state variables towards activity or inactivity, depending on what the current is and what the current state of the state variable is. And so again, this is the transition rate formulation. We'll see on the next slide the steady state formulation. What we also see here on this slide is the definitions of the forward and backward transition rates that were determined by Hodgkin and Huxley. We should note there's the subscript is missing on this alpha and beta, but you use the alpha and beta corresponding to the gate state variable that you're using. And again, these parameters in the form of these equations were fit to empirical data that was collected by Hodgkin and Huxley in their work on the giant squid axon. So here we give the steady state formulation, and that is basically saying the state variable times some time constant tau, s of infinity, is equal to the difference between the steady state value that we want the gate state variable to take on, which is a function of voltage, minus the current state, and this is also controlled by some time constant, which is also a function of voltage. And so the steady state value of the gate state variable is just the alpha function and the beta the ratio of the alpha to the sum of the alpha and the beta function, as before, and the time constant is just the sum of the alpha and the beta function for this state variable. And so we can see this is sort of like charging up towards, as it approaches this steady state value, which is controlled, the rate of change is controlled by this time constant tau. And so this is just another way to formulate that. And I think you can appreciate that, given these definitions of the steady state value and the tau value, that this is just an algebraic manipulation of the transition rate formulation as well. So let's go back to our circuit diagram that now incorporates the components developed by Hodgkin and Huxley. So we have the input current, the capacitance across the membrane of the cell, the leak current, and then the sodium channel and the potassium channel with the variable conductance resistors here. And we see that the rate of change of current, the rate of change of voltage times the capacitance, which is the current through the membrane, is equal to the sum of the ion currents plus the external stimulation current. The ion current is the conductance times the difference between the membrane potential and the reversal potential. And then we have these expressions here for the conductance of the different channels, so leak, potassium, and sodium. And then we have here the dynamics of the gate state variables that affect these conductance values. Now, you may have noticed a picture of a squid here on this slide, and that's because this work was done by Hodgkin and Huxley when they were at the Woods Hole Oceanographic Institute. And they were working with a biological model which was the squid giant axon, which is just literally a very large axon, a neuron that exists in species of squid. And they found this easier to work with because of its physically large size, which was a very convenient model to have, especially if precision manufacturing for building probes and sensors is not quite up to the standard that we have today. So they discovered that modeling the sodium and potassium channels alone, using 6 gating variables, were sufficient to produce the action potential shape that we're trying to reproduce here, that we see in neurons, and we have yet to actually generate with our models. And now they kept the leak term in here to maintain, to allow the membrane potential to return to the resting potential that we expect to see in an actual neuron. All of the constants used in these equations were fit to the empirical data from the squid axon work. But if we wanted to use this model to fit human cortical neurons, then we'd need to generate different parameters to fit the data. However, the general shape of the equation should remain the same. Now, in general, the coupling of all these equations together makes coming up with an analytical solution for membrane potential as a function of time impossible. You may remember from the last lecture we had the constant current model, where we could plot the voltage of the neuron and the leaky integrate and fire neuron as a function of time, and we had an expression for that both when the constant current was applied and when the current was taken away. We aren't able to do that here, and so what we need to do is use numerical integration to figure out what the values of the different parameters should be at any given time. And if we're going to do that, like all numerical integration, we need to make sure that the time steps are small enough that we're actually accurately representing or capturing the behavior of the system. And generally speaking, time steps of about 1/40 or smaller will be sufficient for this task. Now, to understand how all these equations interact to produce biologically realistic voltage dynamics, let's sort of walk through a simulation of the equations for an above threshold input, that is to say, something that will cause the neuron to spike, and examine what the state variables do as the action potential occurs. So what we have here is this top graph is the membrane potential of the neuron. This bottom graph here is the current flow through the M channel. That's the sodium activation channel. And then we have here M sodium activation, M sodium inactivation state variable, and then N the potassium activation state variable. And so we start by injecting a small amount of current at this time here, that this is an external current, that will cause the membrane potential to increase from minus 65 millivolts up to about minus 50 millivolts. And at this value, both M and H have non-zero values, which means that the sodium channel is partially open. And this then creates a positive inward current as the sodium causes the voltage to increase higher. Because remember, the sodium reversal channel is positive 67 volts, 63 volts, and it's trying to, because the channel is open, it's trying to drive the membrane potential up towards that value. So the voltage continues to increase, and it starts increasing more sharply. Because we get a feedback loop. So as the voltage increases, it causes this value to the M starts to increase as well. So more sodium is coming into the neuron. Now this process stops, it halts at positive 50 millivolts or thereabouts. And this is because at this point, the membrane potential is close enough to the reversal current of the sodium, which is in the 60s, that the current through the ion channel starts to decrease and it becomes very small. Right? And that makes, and at this point also we see that the gating variable, the inactivity gating variable for the sodium channel starts to decrease, starts to close off the neuron. And that makes the channel close. And then as the voltage, the membrane voltage is reaching 50 millivolts, positive 50 millivolts, the potassium activation channel begins to open. Right? So we see here. That causes potassium ions to exit the neuron, and that creates a positive outward, that is to say a negative current, driving the membrane potential back down towards negative values. Right, because it's trying to achieve a reversal potential of in the minus 80s. Right? And so this negative current actually causes an overshoot below the minus 65 millivolts, which it then takes time to recover from. This corresponds roughly to the refractory period, and then the N, M, and H parameters all slowly begin to return to their, the M returns faster than H and N, but they all begin to return back to their equilibrium values. And those are, these values here roughly before the current was injected at t equals 5. Now we can retell this using the steady state formulation of the gate state variables. So we see these curves here are the curve of the steady state value of N, M, and H gate state variables as a function of voltage, membrane voltage, and this graph here is a function of their time constants, also as a function of the membrane voltage in millivolts. And we see M here, H has this big peak, and then N follows this curve sort of in the middle. And here we see that M infinity and N infinity, the steady state values, increase as voltage increases, while the inactivation steady state value decreases as voltage. It increases while voltage decreases. So increasing the voltage causes M to increase as it tries to attain the steady state value, and that creates a sodium current that drives the potential to the reversal potential for sodium. And then as voltage approaches the membrane voltage approaches the reversal potential of sodium, we see the conductance of the sodium channel is balanced between M approaching 1 and H approaching 0. So as we go from minus 50 and start increasing. And to see whether the activation gate M or the inactivation gate H dominates, we look at the time constants in the right-hand graph here. And we see that tau of M is much, much, much smaller, which means to say it's faster to change, than tau of H, which means, relatively speaking, M changes faster than H does. This explains why M goes to 1 very quickly, as we saw in the previous slide, while H sort of lags behind, allowing the positive feedback loop during the quick upswing period that creates the action potential. And by the time the potassium channel starts activating, the negative current starts pushing the membrane potential down to the minus 83 millivolts, reverse potential for potassium, and towards the minus 65 millivolt resting potential of the neuron, and that keeps the sodium channel closed while V is repolarizing. But because both tau of H and M are large, that means that the voltage does not immediately settle on the equilibrium point immediately, right? N and H can't respond quickly to changes. So so there will be some overshoot if the potassium channel is open too long and the sodium channel is closed for too long, and that will cause the membrane potential to overshoot past minus 65 millivolts, which is what we saw in the previous slide. However, V doesn't go too negative because as it approaches the reversal potential for potassium, the magnitude of the potassium current approaches 0, and so that current stops flowing, and then over time V recovers from its overshoot towards the equilibrium potential, and this is sort of through the activity, well, in our model, the activity of the leak channel. So these complex interactions of M, H, and N actually explain the refractory period of the neuron. We can do this as a computational experiment, so we see a graph here, where we inject some current at time t equals 20. That's what this arrow indicates, that we're injecting a current. And we see a spike an increase in the membrane potential, and that actually triggers an action potential. But then we enter the refractory period, and we start applying currents, and we don't see an action potential, even if they're the same magnitude as what we indicated when the neuron was at the resting potential. And so we have to ask ourselves, why is that? Well, that's because the voltage has dropped below the equilibrium potential, for one thing. So the same amount of current that caused a spike at minus 65 millivolts will not cause a spike at a lower potential. It's not big enough to get it to the threshold, the spiking threshold. Further, because of the large time constants on tau H and tau N, the potassium channel is staying open, and more sodium channels are closed than would be at rest. So when we increase the potential of the voltage of the membrane, the potassium channel is open to let positive ions exit, and the membrane becomes more negative again. And so after the spike, the state of the gates, the sodium and the potassium gates, are different than what they would be at rest. And sodium is closed and potassium is open, whereas we would expect at rest we'd want the sodium to be open and potassium to be closed, at least initially. And if we want to initiate an action potential. So that means that the negative currents are still dominating, and that causes any perturbations to decay faster and back towards the recovery curve, instead of back towards the equilibrium potential of the neuron. And there's another, and sorry, we should say that this is an interesting explanation. Using our model, we have now explained not only the shape of the action potential spike, but we've also explained the behavior of the refractory period, or at least we have a model that explains, that it produces both of these kinds of behaviors. So there's also another phenomenon called the rebound spike that is an interesting observation we can demonstrate here. So if you stimulate a neuron with a small positive and small injection of current, but it's not enough to cause the neuron to spike, what happens is the membrane potential eventually goes back towards the equilibrium potential. However, if you apply that same magnitude positive input just after removing a suppression of the neuron, so here we're stimulating the neuron, here we're suppressing the neuron, letting the suppression go, and then applying that same magnitude positive spike, positive input, which wasn't enough to cause a spike, we can then generate a spike, one spike. And this activity here is called subthreshold oscillations, and that is to say that it's the dynamics of membrane voltage recovery in the absence of a spike, below the spiking threshold. But these oscillations here under the threshold are also governed by interactions between the M, H, and N gate state variables. And the recovery to the V equilibrium here looks actually like damped oscillations rather than an exponential decay. So in the previous slide, here we see sort of a vaguely exponential decay-like shape. In this, we see that the thing sort of oscillates until it achieves, again, it has sort of this damped oscillation before it achieves the equilibrium potential again. So likewise, when we get the stimulus as a large negative value, and then when it overshoots as it returns back to the equilibrium potential, that overshoot plus whatever our little stimulus is here can be enough to push the neuron past the threshold and get the and to get the actual action potential to be produced. And so gating-wise, when we're holding the membrane voltage below the equilibrium voltage, the minus 65 millivolts, that brings the slow inactivation of sodium, the H gate, closer to 1. And when that inhibition, the negative input, is released, the small excitation is applied, the M opens very quickly, and this M cubed times H that we have in the equation for conductance of sodium, the M really dominates. And this makes it makes it more dominant than it was before, without this negative stimulation being applied. And this makes the positive feedback stronger because H doesn't have time to recover as quickly because of the larger time constant on the H value. And so this can cause a single spike if the stimulus is even if the stimulus is below the threshold for positive current. So here again, with the Hodgkin-Huxley model, we have another explanation, a model that produces biological observations, which again is what we're trying to achieve with trying to model computational models of neuroscience. There are some extensions we can make to the Hodgkin-Huxley model. For one, it's easy to add more ion channels. We only dealt with sodium-potassium plus the leak channel, or leak current. We can add other ions to the model in the exact same way. We just add more parallel paths in the circuit model. Think, a resistor and a battery in parallel to the capacitance. That represents the membrane potential. And so we can just stick on more of these ion channels as we see fit. And we can do this. This will help us fit biological data better. And this is especially useful under non-traditional conditions. We can also add spatial structure to our model. That's what we see up here. What we've done so far is we've treated the neuron as what you might call a point model. The voltage, the gate state variables M, H, and N, they all describe the potential in gating across the entire cell as if it were equal no matter where you probed on the body of the neuron. But all of the physical events we've described with the ion channels and the voltage changes are localized in different parts of the cell. And in actual fact, this behavior is not necessarily uniform across the cell body. So to model this, we will have to change our model of the cell to represent it as many connected compartments. So here we see this sort of repeating pattern of compartments, where each compartment acts like the point model that we have developed for this neuron. And what we're doing here is we're imbuing the model with spatial extent. So it matters where things are happening, and this will let us have a more sophisticated model of neuron activity. And finally, before leaving biologically plausible models, we also want to build a model of how the input spikes cause input currents using a conductance and voltage-based synapse model that has similarities to the Hodgkin-Huxley model. So we talked about how the membrane voltage changes as a result of conductances and membrane voltage. Next, we will talk about how the current, in our H, we had our H and our F model. Today we talked about F. In our H, we will discuss how we can use models of conductance and voltage-based synapses that work in a similar fashion to how the Hodgkin-Huxley model described the membrane potential. So that concludes this lecture. Today we covered ion channels, we covered the role that they play in changing membrane potential, and we worked through the details of the Hodgkin-Huxley model, how they represent ion channel currents using voltage-based conductances, and how they produce dynamics of the action potential itself, as well as explain some experimental observations that we've seen from biology. A good project to come out of this lecture would be to build your favorite detailed neuron model, demonstrate it working. And then also just to keep in mind that assignment 3 is due March 2nd and the project proposal is due March 9th. So thank you, and we will see you in the next lecture.